mixed Nash equilibrium, and these are the topics for today. So we know that a normal form game contains a set of agents, and script A sub I is the action space of the ith agent, and lowercase a sub I is any action of the ith agent, and pi I is the payoff function of the ith agent, which maps a joint action to a real number, and bold lowercase a is a joint action which contains the actions of all the agents. And we know that A subscript negative I is the joint action space of all the opponent agents of agent I, and this is a joint action of the opponent agents, and this is the complete joint action. A mixed strategy is a probability distribution over actions. So this is a mixed strategy of agent I, and for each action that's available to agent I, we have a certain probability. And this is the joint strategy, joint mixed strategy. This is the opponent joint mixed strategy, and this is again the joint strategy of all agents I and opponents negative I. The support of a mixed strategy is this, which is equal to the set of all actions available to agent I such that the probability of the agent picking action AI, in this mixed strategy is strictly greater than 0. So here's an example of what's a joint strategy, what's a strategy, mixed strategy. For agent 1, let's say this is his or its strategy. 1/4 the probability of picking a rock, and 3/4 being the probability of picking paper, and 0 being the probability of picking scissors. And likewise, the strategy of agent 2 is to pick rock, paper, and scissors with equal probability. Now, the support of S1, agent 1's strategy is rock and paper, because only rock and paper have non-zero probabilities, and the support of S2 is rock, paper, scissors, because all three of them are being picked with non-zero probability. Payoffs. Now, suppose we have a set of agents 1 and 2, and their actions are A, B, and P, Q, R. So these are the payoff matrices of the agents P1 and P2. Consider this joint action BR. So agent 1, the action of agent 1 can be represented in this form, and the action of agent 2 can be represented in this form as a vector. Now, don't get confused with this notation. I'm using this E2, E3 to denote which position the 1 is in, just to be compatible with my other courses. Anyway, so the payoff for this joint action, the payoff of agent 1 is E2 transpose P1 E3, which is 3, and the payoff of the other agent likewise is you replace P1 with agent 2's payoff P2, and that's -1. It's actually this 3 and -1 here. Similarly, suppose we have mixed strategies. S1 is 0.4 and 0.6, and S2 is 0.2, 0.3, and 0.5. Then we can compute the payoffs of agent 1 is S1 transpose P1 S2, which is, you can do the math, that's 0.7, and payoff of agent 2 is S1 transpose P2 S2, which is 0.26. Best response. The best response of agent I given uh, the joint actions of the opponents is AI is the set of all actions AI which give the highest payoffs for that agent. Here's an example. Uh, the best response of agent 1 when agent 2 is playing R is C. It's this blue circle here. I know the red circle is overlapping that. And the best response of agent 2 to C is PR. These are the two red circles. Now here, the best response of agent 1 and best response of agent 2 coincide here. And so this is the Nash equilibrium point. So formally, we can define the Nash equilibrium, or rather the pure weak Nash equilibrium as the joint action A star, where each agent is playing its best response to all its opponent agents. Another way of defining it is AI star is Nash equilibrium if the payoff of agent I for any other action AI which is not Nash equilibrium is less than equal to payoff with the Nash equilibrium, and replacing this less than equal to with a strict less than, we get the definition of a strict Nash equilibrium. Consider the game of rock, paper, scissors. We know that this game has no pure Nash equilibrium. Here, anyone who has played rock, paper, scissors understands that the best strategy is to randomize, pick rock, papers, or scissors with equal probability of 1/3. And that's the Nash equilibrium strategy, as we shall see later. So the Nash equilibrium strategy of both agents is to pick each action RPS with equal probability of 1/3. Now suppose agent 2 plays only rock and paper with equal probability of half and never plays scissors. In that case, what's agent 1's best response? It can easily be seen that agent 1's best response is to play paper P only, because if agent 2 plays rock, then agent 1 wins, and if agent 2 plays paper, then it's a tie. So agent 1 wins half the time, and it's a tie half the time, and it's therefore the best response of agent 2 is to play only paper. The payoff of agent 1 under these circumstances is half, because he wins half the time and it's a tie half the time, and for agent 2 it's negative half. So we can now formally define a mixed strategy Nash equilibrium. So S star is a mixed Nash equilibrium if for each agent I, the payoff at Si star is the highest over all other mixed strategies. In other words, if Si is another mixed strategy of agent I, which is not the Nash equilibrium mixed strategy, S star I, then the payoff pi I with this mixed strategy Si is always less than equal to the payoff of that same agent I with the Nash equilibrium mixed strategy S star I. And furthermore, replacing the less than equal to sign with a strict less than sign, we get the definition of a strict Nash equilibrium. Note that a pure Nash equilibrium is a special case of mixed Nash equilibrium. And we've already seen the definition of a support. So some actions are in the support of the Nash equilibrium strategy of an agent, and some actions might not be. In the rock, paper, scissors game, the Nash equilibrium strategy is one third, one third, one third rock, paper, and scissors, and the expected payoff of either player at equilibrium is 0. Expected payoffs. We've seen informally how to compute the expected payoff given joint strategies for a bimatrix game previously. Now, given any joint strategy S, what's the probability of the joint action A? Now, obviously, each individual agent's action AI must be in the support of its strategy SI. Otherwise, the probability of AI, if it's 0, then the probability of the whole joint action A is also 0 because it's the product of probability of A sub I given S sub I. Now, this is not really a conditional probability. Treat it as some informal notation. So in S of I, what's the probability of A of I? That's this, and the product of all those probabilities of all the actions of each agent I in A, that gives you the joint probability. The expected payoff of agent I given the joint strategy S is the summation of the payoff of that agent under action A times the probability of action A happening under the joint strategy S. We can express the expected payoff in this manner too. Here, this is the probability of the joint action AI comma A sub negative I and the probability of that joint action. Here's an example. So these are the payoffs here, and X and 1 minus X are the probability of this first agent, the row agent, to take this action and this action. And likewise, Y and 1 minus Y are the probability of this agent 2 here to take action, the left action and the right action. So the probability of this action, let's call this action top and this action bottom for the first agent, and this left and this right for the second agent. So this joint action top left, what's the probability? X times Y, and the corresponding payoff for agent 1 is 1. So 1 times XY, it's one of the terms here. We are doing this summation here. And plus probability of top and right is X1 minus Y, and the corresponding payoff is 2. So 2 times X1 minus Y plus probability of bottom left is 1 minus xy, and the payoff is 2. So plus 2 times 1 minus xy, and for the last joint action is bottom right, the probability is 0. Sorry, the probability is 1 minus x, 1 minus y, and the payoff is 0, so we get this term. And likewise, for the second agent, the payoff for top left is 1, and the probability of that action is xy. For top right, the payoff is 0, and the probability is x 1 minus y, and it's -1 for bottom left, and the probability is 1 minus xy, this term, and likewise 0 times 1 minus x, 1 minus y for the last term. So these are the expected payoffs from this game with these probability x1 minus x and y minus 1 minus y. I'm writing down the payoffs here to make space below. So the payoff of agent 1 was this, which simplifies to negative 3xy plus 2x plus 2y plus 2. And agent 2's payoff, likewise, simplifies to twice xy minus y. Now, from the definition of NE, we know that each player or each agent I tries to adjust its own strategy to maximize its own payoff. In other words, pi I, the payoff of agent I with respect to its strategy Si, any other strategy Si is always less than equal to its payoff with respect to its own Nash equilibrium strategy Si star. In other words, Si star equals argmax with respect to Si of pi I of Si comma Si star. Note that this is unilateral. So the strategies of the opponent agents are the same. This here S negative I star, and this is S negative I star. So the opponents still play the Nash equilibrium, and each agent tries to adjust its own strategy Si to maximize its own payoff. So let's assume in our little example that X star, Y star is the joint strategy at Nash equilibrium. So agent 1's payoff is this, and agent 1 can adjust its payoff with respect to only X star. Whence, how do we obtain the maximum of its payoff pi 1 with respect to X? We simply take the derivative in this simple case. So derivative of pi 1 with respect to x must be equal to 0 in order to maximize pi 1. Whence, differentiating this, we get negative 3y star plus 2 equals 0, whence y star equals 2 over 3. In a similar manner, agent 2 has only y in control, right? So agent 2 tries to maximize its payoff with respect to y. Therefore, taking the derivative of pi 2 with respect to y, we get 2x star minus 1 equals 0 at NE. Therefore, x star equals half. So the Nash equilibrium is, we can write it simply as x star y star, which is half and 2/3, or 0.5 and 0.67, or more formally, we can write them as vectors. So S star is X star 1 minus X star, and uh, Y star 1 minus Y star, which is this 0.5, 0.5, and 0.67, 0.33. There are other ways to compute the NE by using simple observations. We take these techniques up next. The payoff is indifferent to all actions in the Nash equilibrium's support. For instance, in a game of rock, paper, scissors, as long as the opponent picks randomly with one-third probability uh, rock, paper, and scissors, it doesn't matter to an agent whether it picks rock or paper or scissors. The expected payoff in each case will be exactly the same, which is 0. In other words, if AI star and BI star are two actions in the support of SI star, then the payoff pi I given um, AI star for this action AI star um, given the opponents are playing the Nash equilibrium strategy is the same as that of uh, agent I when playing B I star, and again as long as the opponents play S negative I star. In other words, all actions in the Nash equilibrium support have equal payoffs. We've also seen before that strictly dominated actions cannot be in the support of a Nash equilibrium. In other words, if there's some action AI that's strictly dominated by some other action A prime I, then this action AI cannot be in the support of the Nash equilibrium strategy of the ith agent. Now, these two really small theorems or lemmas, if you want to call them that, are useful in computing Nash equilibria of different games, as we'll see next. So let's see how to compute the NE using the principle of indifference. So we have two agents here, the row agent, agent 1, and the column agent, agent 2. And the actions of agent 1 are up and down. And those of agent 2, the column agent, are left and right. So the probability of picking up and down are x and 1 minus x by agent 1, and for picking left and right by agent 2 are y and 1 minus y. Now, suppose the agent plays u up, then the payoff would be the other agent plays left with the probability of y and right with the probability of 1 minus y. And so for up, the expected payoff would be y times 1 plus 1 minus y times 2. Y times 1 plus 1 minus I times 2. So y plus twice 1 minus y, which is equal to 2 minus y. In a similar manner, if agent 1 plays down, then the payoff of agent 1 would be y times 2 plus 1 minus y times 0, which is twice y. Now, from the principle of indifference, the payoffs of both up and down would be the same. Therefore, 2 minus y and twice y would be whence at equilibrium we would have 2 minus y star is equal to 2y star, whence y star is 2/3. So the probability of picking left is 2/3 and the probability of picking right is 1/3. That's for agent 2. Let's proceed and find out what x and 1 minus x are. Now, considering agent 2, when playing left, which is with the probability of y, of course, the payoff would be x times 1 plus 1 minus x times -1, which is this, twice x minus 1. And when playing this strategy right, payoff in both cases are 0, so payoff is 0. So what we must have, as using the principle of indifference, is that twice x minus 1 must be equal to 0, whence x star is equal to half. So this is the Nash equilibrium of this game, half and 2/3. In other words, agent 1 plays up with a probability of half, and agent 2 plays left with a probability of 2/3. We also know that we can remove strictly dominated actions without affecting the Nash equilibrium. So let's look at this one. Agent 1, the row agents actions are up, middle, and down. Sorry, I have a B here. It should be a D. And agent 2, the column agents actions are left, middle, and right. Now we can see that for agent 2, right dominates strictly over M. M2 is agent 2's M because we have two M's here, M1 and M2. So that's because 7 is greater than 6, 3 is greater than 2, and this 3 here is greater than 2. And so we can eliminate this action for agent 2, resulting in this simpler game. And now the simpler game here reveals more dominance relationships. So you can see that down, D actually, here is dominating M1 because 4 is more than 3 and 0 is more than -1. So we can also eliminate this middle for agent 1, yielding this even simpler bimatrix game. Now we can proceed to find the Nash equilibrium of this bimatrix game. That's the next example. So now the probabilities of up and down actually, D, not B, are x and 1 minus x for agent 1, and the probability of left and right are y and 1 minus y for agent 2. So for agent 1, the payoff with up would be 0 times y plus 2 times 1 minus y. That's this, 2 times 1 minus y, or 2 minus 2y. And for picking down, this down, the payoff would be 4 times y plus 0 times 1 minus y, whence payoff is 4y. Now, from the principle of indifference, for the joint, if both of these are in the support of Nash equilibrium, then we must have 2 minus 2y should be equal to 4y, whence y equals 1/3. Similarly, the payoff of agent 2 for playing left is equal to 0 times x plus 6 times 1 minus x, 6 minus 6x. And for playing right, the payoffs are 7 times x plus 3 times 1 minus x, 7 times x plus 3 times 1 minus x, which is 3 plus 4x. And equating the two, we have from the principle of indifference, x equals 3 over 10. But are we missing something here? We got a mixed Nash equilibrium, 3/10 and 1/3. But you can see that there are two pure Nash equilibria for this game too. So let's proceed in the next example to analyze what's happening graphically. So the Nash equilibrium is when y is 1/3, so that the left action is picked with a probability of 1/3 and the right action is picked with a probability of 2/3. Now let's look at agent 1's payoffs. When suppose y is less than 1/3, in other words, agent 2 is picking right more often than at Nash equilibrium. So what happens then? When y is less than 1/3, it turns out that the payoff of agent 1 for playing up, which is 2 minus 2y, since y is less than 1/3, it's more than the payoff of agent 1 when playing down. Therefore, the best response of agent 1 when agent 2's strategy is y less than 1/3 is to play the one of these two which has the higher payoff, which is up. In other words, agent 1 will pick up necessarily all the time. X equals 1 in this case. So this is what we have. And of course, when y is 1/3, which is at Nash equilibrium, then x is 3/10, which is graphically, since we're illustrating it, I'll just write it in this manner. 0 is strictly less than x, which is strictly less than 1. Likewise, when y is greater than 1/3, so y, this left is being picked more often than at equilibrium. So now let's examine the payoffs. When agent 1 plays up, the payoff is 2 minus twice y, and the payoff when playing down is 4y. And now, since y is more than 1/3, 4y here is more than 2 minus 2y. Therefore, the payoff for playing down is more than the payoff for playing up. Therefore, the best response of agent 1 is to play down with a probability of 1. In other words, 1 minus x should be equal to 1, or x should be equal to 0. That's shown right here. X equals 0 when y is greater than 1/3. Now let's examine the payoff of agent 2 for different values of x. We know that at Nash equilibrium, agent 1's strategy is to randomize, with x being 3/10 and 1 minus x being 7/10. So 3 out of 10 times it plays up, and 7 out of 10 times it plays down. What would agent 2 do when x is less than 3/10? So this up is being picked more often than under Nash equilibrium. So what will happen here is, let's look at the payoffs. When agent 2 plays left, the payoff is, we saw before that it was 6 minus 6x. And when agent 2 plays right, the payoff is 3 plus 4x. And since x is less than 3/10, this is more than this. So 6 minus 6x is more than 3 plus 4x. Playing left yields a better payoff than playing right from agent 2's perspective. Therefore, agent 2 should always pick left. In other words, left, this is left, will always be picked. So y equals 1. So when x is less than 3/10, y is equal to 1. And of course, when x equals 3/10, then this is the Nash equilibrium. So y should be between 0 and 1, strictly between 0 and 1. In fact, it is 1/3. Finally, when x is greater than 3/10, then the payoff for playing right, which is 3 plus 4x, is more than the payoff when playing left. So agent 2 should pick right. Hence, 1 minus y should be equal to 1 if the agent picks right all the time. So y equals 0. This is when x is greater than 3/10. This is the graphical illustration of the best response of agent 1 when agent 2 plays y for different values of y. Now this is when y is 1/3. And when y is less than 1/3, we are here, y is less than 1/3, then the best response is for x to play, for agent 1 to play up with a probability of 1. So x equals 1 is the best response. Now, for 1/3, maybe I should have used dotted lines here. This is discontinuous. In fact, there is only one point here, which is the mixed Nash equilibrium, 3/10. And then for y, so this is this point here. And for y greater than 1/3, this side, x must be equal to 0. So x is equal to 0. When y is greater than 1/3. This is the y-axis and this is the x-axis. It's a little confusing, but I thought that's the best way to represent this because x is dependent on y here. So now let's look at the best response of agent 2 when x is varied between 0 and 1. So when x is less than 3/10, we know that y should be equal to 1. So when x is less than 3/10, it's this region here, then y is equal to 1. When x is exactly 3/10, then we know that y should be 1/3. So it's between 0 and 1. So I draw this horizontal line. And then when x is greater than 3/10, so x is between 3/10 and 1, then the best response is y should be equal to 0. So y equals 0. This is y equals 0, and this is y equals 1, of course. So this red curve is the best response of agent 2 to x. Now we superimpose the two best responses. And we know that at Nash equilibrium, pure or mixed, each agent is playing its best response. So there are, in fact, 3 points of intersection, this, and this. And at these 3 points, both agents are playing their best responses. Therefore, These 3 points are the 3 Nash equilibria. This is the mixed Nash equilibrium that we got previously, and these are the 2 pure Nash equilibria, this and this. Why is it that when we applied the principle of indifference earlier, we could not get this and these 2 pure Nash equilibria? Here x is 1 and y is 0, and here x is 0, y is 1. These correspond to these 2 here. Why is it that we never got these 2 Nash equilibrium points when we applied the principle of indifference? That's because when we assumed the principle of when we applied the principle of indifference, we assumed that for agent 1, both up and down were in the support of its Nash equilibrium strategy, and likewise both left and right were in the support of agent 2's Nash equilibrium strategy. But look at here, at this equilibrium, this pure Nash equilibrium, the value of x is 1 and the value of y is 0. So when x is 1, agent 1 is not playing down, it's only playing up. So down is not in the support of this Nash equilibrium, and likewise y is 0, so agent 2 is only playing right. So left, this is not in the support of this Nash equilibrium, whence we could not apply the principle of indifference in that case. And the same argument holds for this pure Nash equilibrium, because x is 0 and y is 1. So agent 1 is always playing down and agent 2 is always playing left. The other 2 actions, right and up for agents 2 and 1, are not in the support. Lastly, every game has at least one Nash equilibrium. This was proved by John Forbes Nash, and we shall look at informally the proof in the next lecture.